Welcome to this module on GPU-centric AI compute fundamentals. Today, we will examine the concept of latency, specifically focusing on why minimizing it is absolutely critical for the performance of distributed AI training workloads. To understand the importance of latency, we must first recognize that AI training is fundamentally a distributed computing problem. We are not running these jobs on a single machine. We are distributing the workload across multiple interconnected nodes because the models are simply too large and complex. In this environment, the network acts as the backbone of the data center. Thousands of GPUs must work in concert, frequently pausing their computations to exchange huge amounts of data. If this communication is slow, the entire training process suffers. Therefore, the network's ability to handle this distributed load efficiently is just as important as the speed of the GPUs themselves. This diagram visualizes the distribution of an AI workload. A massive AI model is split into shards and distributed across multiple GPU nodes, 1, 2, and N, via the network fabric. The arrows between the nodes represent the constant synchronization of parameters required during training. This shows that the nodes are not independent. They are tightly coupled and rely heavily on the network to stay in sync. Traditional web applications, average latency is a good metric. In distributed AI, it is meaningless. Here, the runtime of a distributed task is governed strictly by the slowest participating node. We call this tail latency. It is the time it takes for the very last message to arrive. Imagine 1,000 GPUs finishing a calculation. They cannot proceed to the next step until the last packet from the slowest node arrives. Network congestion or deep buffers cause even one packet to be delayed. Valuable GPU resources sit idle, waiting. Therefore, consistent low latency is far more valuable than high average speeds with occasional spikes. This Gantt chart demonstrates the impact of tail latency. GPU 1 and GPU 2 finish their compute tasks quickly at the 5-second mark and enter a wait for sync state. However, GPU 3 experiences a network delay, the tail latency, pushing its completion to 9 seconds. The entire training step cannot complete until GPU 3 is finished. This visualizes how one slow path forces the rest of the cluster to idle, wasting compute cycles. Learning frameworks rely heavily on collective communication algorithms, such as all-reduce and all-to-all. These aren't simple point-to-point transfers. They involve complex data patterns where every GPU shares data with every other GPU. This requires tight synchronization. If your network has high latency or jitter, you break this synchronization. This prevents the system from efficiently overlapping computation with communication, which is a key optimization technique. Furthermore, using deep buffer switches to absorb bursts might seem like a good idea, but they actually increase tail latency, which directly drives up the job completion time or time to train. This sequence diagram shows an all-reduce operation. GPU and GPU-B send gradients to the switch. Ideally, the switch forwards the data instantly. However, if there's processing delay or buffering in the switch, represented by the high latency delay note, the return of aggregated data is delayed. Consequently, the next compute cycle for both GPUs is pushed back, illustrating how network latency directly stalls the training process. To combat latency, we deploy specific technologies. First, we use remote direct memory access, or RDMA. This allows data to move directly from the memory of one GPU to another, completely bypassing the CPU and the OS kernel, which significantly cuts latency. Second, we implement lossless networking to ensure zero packet loss, because retransmitting dropped packets causes massive latency spikes. We also use in network computing, which is NVIDIA Sharp. This offloads collective operations to the switch itself, reducing the amount of data traversing the network. Finally, we utilize cut-through switching, which forwards packets immediately without waiting for the full frame to arrive. This comparison highlights the efficiency of RDMA. The top path shows the traditional method where data must pass through the source CPU, the network, and the destination CPU before reaching memory, adding significant latency at each step. The bottom path shows the RDMA low-latency approach. Data moves directly from source memory to the network, enhanced with Sharp, and straight into destination memory, bypassing the CPU bottlenecks entirely.